crucial moment for climate action. To stabilise the climate, we must stop using fossil fuels in our cars and homes. Chemistry is electrifying society's transition to net zero, powering new innovations in batteries and energy storage. Scarce elements at the heart of these technologies must be sustainably sourced, used and reused. Get involved. Sustainability. Powered by chemistry.
Hello everyone, and welcome to the Royal Society of Chemistry's live event showcasing cutting-edge sustainability research. In the next hour, we're going to hear from researchers about their work, which is being published in our new open access journal, RSC Sustainability. Today, we're going to get to discuss innovative methods for recycling technology metals and plastics, improving chemical production processes to minimize pollutants, and new pathways to shift from fossil fuels to biological feedstocks. This seminar is being recorded, so you can watch it back later if you wish to, or you want to share with colleagues and friends. And as we're live on social media, you can actually join the conversation and ask questions, which we'll try to pick up and get to our speakers. So before we start the discussions, I'd just like to introduce some of the foundations of sustainable chemistry. And so let me just share my screen. There we go, that's taking a moment. There we go. Right, so I want to talk to you about my view of sustainable chemistry. And in 2004, I became the world's first professor of sustainable chemistry. And this is kind of how that came about. And this, for me, really is the start of my journey in sustainable chemistry. And in 1987, the UN issued this report, Our Common Future, often called the Brundtland Report or the Brundtland Commission. And it was looking at what it meant to have sustainable development. It's a lengthy report and you can't really summarize that too easily in one sentence, but here's my attempt to do so. And in this report, they came up with this idea, which was sustainable development was development that met the needs of the present generation without compromising the ability of future generations to meet their own needs. And that idea, in its elegance and simplicity, really grabbed hold of people. And very shortly after this, we started people from the chemical sciences community to talk about how chemistry can contribute to this. And it kind of took two forms. So the first, and perhaps, superficially most obvious, is that sustainable chemistry is then the implementation of that idea of sustainability in the production and use and eventual recovery or whatever of chemicals. And though the application of chemistry and chemical products to enable sustainable development to occur. More recently, we think about sustainable development in the terms of the Sustainable Development Goals. There are 17 of them. I'll come back to that in a minute. But whenever I find myself talking to people about chemistry and sustainable development, they always focus first on this. Number 12, responsible consumption and production. And within that, even the targets. And so there are a number of targets under this, but I want to particularly pick out this one in red. And this is target 12.4, and I shall read it, is by 2020, that is 2 years ago, we will have achieved the environmentally sound management of chemicals and all waste throughout their cycle in accordance with agreed international frameworks. And I'll leave you to read the rest. And so, vitally, I think you'll agree with me, we have already missed this deadline. But bringing us back to the wider Sustainable Development Goals. I would say, there are some here which are, obviously very technical, and you can immediately see in number 7, affordable and clean energy, that chemistry and chemical scientists have a great deal to offer. But I would also to propose to you that even the more society-based ones, like gender equality or reduced inequalities, chemical scientists have a great contribution to make to these as well. So I truly believe that chemistry and chemical scientists have a contribution to make to all 17 of these goals. And for me, that's what sustainable chemistry is. One way of viewing sustainable chemistry, which is really starting to come to the fore now, is thinking about chemistry's response to the transgression of planetary boundaries. And there has been a very interesting paper on this by Stephen Maitland and his co-workers, recently produced in Chemical Science, and the references at the bottom of the screen there. And it talks about planetary boundaries. It identifies 9 of them. But for instance, that might include the ozone layer, biodiversity, ocean acidification, or the use of plastics. And the concept is there are boundaries within which the Earth is able to successfully mitigate and any of what we put into it. And there, beyond those boundaries, now the Earth cannot do that. And we're starting to see that in several areas. So rather than listen to me, I shall stop sharing my screen and you can listen to Stephen Maitland.
The planetary boundaries framework has been a concept that since 2009 has gained increasing attention and recognition as a very broad framework that not only points to individual crises in different elements of Earth systems, but also explains the ways that they're connected together. And one of the very striking things when you start to look at the planetary boundaries is the extent to which chemistry is intimately involved in how these boundaries operate, how the Earth systems operate, for which the boundaries have been set. Our call is addressed primarily to chemists and to say it's now time for change. And we emphasize that this change must involve all branches and levels of chemistry. It's not just for the research chemist or for industry, it's for everyone. And so we talk about the ways that education must change fundamentally to prepare our future generations of chemists for being able to use the tools available as sustainability tools in order to change the ways that they think about chemistry and think about what chemistry can do. There needs to be change certainly in the research areas with a focus particularly on what can be sustainable, but also, of course, big changes in industry and the practice of chemistry to ensure that we move away from the unsustainable methods. So we call for action on all these 3 fronts as being critical to getting out of the situation we're currently in.
So joining me today to discuss the papers that we're going to see and reflect on what that means for chemistry in the future of the world are Professor Fran Kerton and Dr. John Broderick. So perhaps, Fran, if you could introduce yourself first.
Yes, so I'm a professor of chemistry at Memorial University of Newfoundland in Canada. I've been here for about 17 years and I currently supervise a research team of 7 graduate students doing research broadly focused on sustainability, including catalytic transformations of carbon dioxide, finding use for waste from the seafood industry here, and also work on degradable and recyclable polymers and natural polymers like carbohydrates.
And John?
Hi everyone, my name's John Broderick. I'm the Net Zero Programme Manager in our Policy and Evidence team. And so I work on helping to reduce the emissions of the Royal Society of Chemistry through its activities to help us to achieve our goal of net zero operations by 2040. And I help to follow and shape our voice and influence on climate change and energy policy.
Right, so now we're going to introduce some clips from authors from papers that have just been released by RSC Sustainability. While you're listening to the video clips, there should be a QR code. And if you'd like to read the full paper, just follow that to the open access papers. So that's free for everybody to read. So the first paper introduces the phytonickel catalyst for processing plastic waste. This has been developed by Professor James Clark's laboratory and is, as he says, triple green. And you can see that in the video.
So we've been working for, about best part of 10 years now on an area called PhytoCat, which is basically taking advantage of the ability of plants to naturally capture metals. And that's been known for some time. But our idea was to our novel twist on this, if you like, was to take the materials that you make from that, the plant with the metal inside it, and not simply burn off the plant to recover the metals, but to try to actually use the metal inside the plant in some constructive chemistry way. In particular, we wanted to use it as a catalyst. So basically, we're trying to find new greener catalysts for important processes, which have a green chemistry relevance, but also to avoid using virgin metals. So we're trying to do several things at the same time, hence the triple green idea. Nickel is actually present in very large amounts naturally across soils in many parts of the world. In fact, nickel is the primary metal contaminant present in surface soil. So when you're looking at contamination, nickel is the first thing you often look for. And there's areas of the country, areas of the world, in parts of Southeast Asia, parts of Australia, parts of Europe as well, where nickel is particularly abundant and covers large areas of land. And the problem there is that it's not just actually sort of getting in the way, it's also actually making it toxic. So they can't use such areas for growing food. So there are surprisingly large areas of land, several percent of the world's total land surface, are made unavailable because of contamination, in particular from nickel. So we thought, great, well, if we can actually remediate the land and also get something which could be useful as a catalyst, fantastic. So we applied our same principles, our same practices. We developed plants which actually were very good at capturing the nickel. We then sort of refined a process so the nickel was going to come out in a useful form. We then turned the plant with the nickel into catalysts, and we started to develop them. And we found they actually did work in a number of applications. In particular, we found they're very good for helping to depolymerize plastic wastes. Although plastics like polyolefins are quite simple in their structure, I mean, they contain the same repeating unit in most cases. The reality is that when you try to break them down, you don't just get the original monomer back again. You tend to get complicated mixtures. So that was always going to be the case. So the challenge was really, can we get something from waste plastics, especially waste polyolefins, because they're the biggest, which actually could have some value. So the idea was, well, nickel, of course, is also known for example, for helping to catalyze carbon-carbon bond breaking, for example, in some cases, and also to catalyze other processes like hydrogenation, which can also be very useful in the sort of valorization of waste streams, including waste plastics. So we found that with waste polyolefins, yes, you can, by changing the catalyst, the amount of catalyst, the activation temperature of the catalyst, the conditions of the processing, we could actually start to get some reasonably promising selectivity when it came to what we make from the waste polyolefin plastics. And also, we also use microwave technology as well, because microwaves are a very focused way of getting heat into the system. So again, fairly well known among the chemistry community is the use of microwaves. So we don't have to use microwaves. You can just do conventional pyrolysis. But we thought microwaves are quite good at generally keeping conditions down. And actually we found, in fact, the combination of these nickel catalysts and microwave enabled us to get depolymerization of things like polyolefins at surprisingly low temperatures. And by working at lower temperatures, you're probably going to get more selectivity in terms of what you make. I mean, if high temperatures, a lot of gasification, which could be useful, but I mean, it kind of limits your potential uses of what you get from these waste plastics. So this way we can tune the process a bit better. We can get higher gas if that's what we want. We can get more liquids if that's what you want. And we can maybe even start to tune the chemicals in there. Now, it's not perfect. We're still getting mixtures, We think the mixtures are a little bit simpler than you can from more conventional processes, but we'd like to think you could do even better.
Well, before I start talking about Jim's paper, it's amazing that we can already see that we've got Mama Amma, who is listening to us from Costa Rica on behalf of the Commission for Sustainable Chemistry, and Amulara Aboje, who's listening from Nigeria. So already we're both good morning and good evening in our global reach, which is fantastic. But to Jim's paper, so one of the things I really like about this paper is, for me, it really does express what I was saying in my presentation. And so of course it is about finding some way of tackling the plastic pollution crisis, and by converting waste polyethylene into high value products. And so that would sit very much in our SDG 12, wouldn't it? I mean, but actually it has such further impact. And, you can see how it's important for SDG 7, affordable and clean energy. Metals like nickel are vital metals for all of our microelectronic and indeed macroelectronic products. And we do have to find a way of being able to mine our own waste, and we'll see more of this later, to be able to mine our own waste in order to deal with both scarcity, but also the incredible environmental cost of mining directly from the planet. So affordable and clean energy. Life on land. He talked about the impact of nickel on agricultural land, and so zero hunger. Industry, innovation and infrastructure. Climate action, because of course one of the places where we find these metals is in our wind turbines. And in order to enable our transition to a low carbon, no carbon, net zero economy, absolutely we need to do all of these things. And so Jim, on my count, I think he's on 5 of them. And so this is exactly the kind of thing that we're thinking about at RSC Sustainability, about being able to cover a huge range of SDGs actually with one piece of work. I don't know, John, Fran, what do you think?
Yeah, Tom, I entirely agree with you. And I think it links really well with some of the themes in Stephen Matlin's paper that he spoke about earlier in terms of planetary boundaries. So that concept has been around in Earth system science since 2009, but the latest paper that's in chemical science there really brings it home to focus on the role of chemistry in the chemical sciences. And so when we start to think about the scale of material flows that go through the chemical industry and the chemical processes, we see that they've doubled from 2000 to 2017 and are expected to double again in coming decades. And James Clark's paper speaks to how we approach those thresholds, both in terms of the pollution of the environment, but also, as you say, finding new uses, new compounds, new systems that can avoid us pushing through further other planetary boundaries, like climate change, which is one of the ones that we're very close to exceeding.
Yeah, so I just want to add to that I really liked in this paper the fact that he was basically remediating by removing nickel that was a pollutant, and then in kind of one step making this catalyst that could target another area of problems, in that we need to find things to do with plastic waste. And a lot of effort is made by chemists worldwide trying to make new catalysts for processes. And this was a really, I thought, very simple approach that was very sustainable by using the plants to accumulate this nickel that could then be used in catalysis.
So yeah, I mean, he's triple green, so it certainly hits that target, doesn't he? All right then, so our next clip is of Dr. Sostin Ung talking about his paper, From rocks to bioactive compounds, a journey through the global phosphorus 5 organophosphorus industry and its sustainability.
One very interesting thing was to see what were the industrial synthetic routes to go towards those useful value-added chemicals. And what we found is that the processes used are usually involving phosphate rocks. So that's the only resource we use right now. Back in the days, it used to be, bones or even urine or guano. But right now, what we're using ever since the late 19th century is phosphate rocks. Those resources are very asymmetrically distributed around the globe. So it's mostly in Morocco. And the problem we have right now is that most of the processes that we use to functionalize and treat all that phosphate rocks and turn it into value-added chemicals is energy costly. It will use a lot of toxic intermediates. It will create a lot of toxic byproducts, and it mainly relies around three very harmful intermediates, which would be white phosphorus, phosphorus trichloride, and phosphorus oxide trichloride, like phosphoric chloride. All three of those are very toxic, not easy to handle, and going through those intermediates to go through either trivalent phosphines or pentavalent phosphorus compounds is a bit complicated because the redox efficiency or the pre-functionalization that you would need is not efficient in terms of sustainability. The hypophosphite way is very interesting. It was developed by Jean-Luc Monchamp from Texas. This route is very promising to create more sustainable alternatives for the synthesis of more higher oxidation state phosphorus molecules. Hypophosphite is already some sort of, it's easy to get from white phosphorus. Those are processes that are already industrial and already well known. What Jean-Luc Monchamp developed was all the different kind of functionalization from the hypophosphite, this new intermediate, and this is very exciting.
So we've heard just how important phosphorus is as an element. So Fran, over to you. What do you think?
Oh, I really enjoyed reading this paper, partly biased from nationality being in Canada. It's from a great group at McGill University. And I think it really shone a spotlight on the fact that we need to not only look at the carbon cycle and keeping that within the planetary boundaries, but also need to consider other elements. So if phosphorus is released into the environment, it can lead to eutrophication. And as Dr. Ong mentioned, the sources of phosphorus that we can use are asymmetrically distributed around the world. And so many of us can kind of focus in on SDG 12 as something important in terms of chemistry, but chemistry can play a role in many areas related to sustainability. And in this case, even SDG 16 that's related to peace, because we all need to start thinking about interesting ways of reusing elements such as phosphorus, or new sources of those elements like phosphorus. So one of my students is processing fishery waste, and in that fishery waste is the bones that have hydroxyapatite, and so we're interested in accessing that phosphorus there. And so I think this paper is kind of like a call to arms, because the interest and level of research going on into recycling and new sources of elements is lagging behind for things like phosphorus. And so I think it might spark a lot of interest and inspire others to work in this area. I don't know what anybody else's thoughts are on this paper.
So I think I think that, I agree with you. We know a lot about the carbon cycle. We teach a lot about the nitrogen cycle. And then we tend to flip, don't we, to the extremely rare elements and start worrying about dysprosium. But there, you know, phosphorus is an example of a really important, you know, it's not rare in that sense as an element, but it is, you know, vital and difficult to access. And we should really think about the phosphorus cycle in just the same way that we do about the other kinds of cycles. I don't know, John, what do you think?
Well, it points to something that's a kind of a tenet of green chemistry about finding ways of being benign by design. And so looking for production pathways that don't create problems that you subsequently need to mitigate. And if I might plug the next panel that we've got coming up on Tuesday, where I'll be discussing low carbon hydrogen with Jonathan Oxley from the CBI. The other major fertilizer that we use, the nitrogenous fertilizers for food production, are currently produced by a highly energetic and highly polluting Haber-Bosch process. And so we've got a speaker there who's talking about benign by design, low temperature catalytic system to help to unlock another important elemental pathway without causing a pollution problem.
Yeah, and I think, you know, I mean, I think it's also worth saying that one of the things that this review shows us is actually just the beautiful chemistry of phosphorus. and it really, you know, I guess I'm showing my, well, conscious bias as an inorganic chemist, aren't I? You know, it does have some amazing chemistry. All right, then. So now we're going to hear from Professor Yutaka Amo and Mika Takeuchi of Osaka Metropolitan University, who are going to introduce their work on a new synthetic pathway to fix CO2 into biopolymers.
I think the CO2 utilization is very important for the SDGs development. So, but now the trend of the CO2 utilization is C1 chemistry, so methanol, formate, and carbon monoxide. So this compound is only to use the fuel, but we devoted to the novel organic material produced by the CO2 and bio-based, such kind of the biomass derivative, simple organic compounds. Thus, this system, the CCU technology, and moreover the CCS, so carbon dioxide captured and stored into the organic compound.
Fumarate is an extremely unsaturated carboxylic acid that is raw material for polybutyrene succinate, a non-unsaturated polyester resin, and a biodegradable polymer. Fumarate also can be isolated in water due to its structural property of having double bond and being trans. Currently, fumarate is synthesized mainly from petroleum resources, which emit large amount of CO2 during the production process. So in this study, we aimed to produce fumarate in water media using CO2, a substance that causes global warming, and pyruvate, a biomass-derived compound, as alternative raw materials to petroleum resources.
And just to prove the point of the previous paper, we now have one on phosphate-induced enhancement of fumarate production. So, John, what do you think of this?
Well, I think this is pointing us towards a family of chemical reactions that are going to be really kind of increasingly important, because most of our focus in reducing climate change emissions is around the energy system. But we equally need to think about all of those really valuable carbon-containing molecules that we use in society, in polymers, in pharmaceuticals, in not just in the energy system. And if we want to stabilize the climate, we need to get to net zero greenhouse gas emissions, and that means largely eliminating fossil fuels. And so if we want to keep using these carbon-containing molecules, we're going to have to find new sources of them, coming either from waste gases, like from cement production, or using bio-derived feedstocks from agricultural wastes or grown crops. And so this paper's great because it shows some of that chemistry about how we can take a waste, a CO2 waste, and put that into a useful pathway to produce a biodegradable polymer. So in this case, the PBS polymer that can produce a heat-resistant plastic for cups and cutlery and food trays and the like, that is subsequently compostable. And they're doing this in relatively low intensity conditions. It's an enzyme system. It's using interdisciplinary work, drawing on biochemical pathways and biological catalysts so that it operates at 30 C instead of 150 or 200 C like the fossil pathways would be. And so, yeah, so I think it's really exciting and stands to point us towards some of the new organic chemistry that we're going to need for a net zero society.
Thanks, Fran. What do you think?
No, I found this really interesting because some of my own research is on CO2 utilization. And so the use of enzymes in this way to incorporate CO2 to kind of fix it in an organic form so it won't be released into the environment is really useful. I'm part of a network that focuses on utilization of CO2 in industrial processes. And so sometimes people question whether it will even be feasible or economically viable to, use CO2 to make chemicals and polymers and drugs and all sorts of things. And it really is. There's been economic analysis done by environmental economists, and using green energy sources, so solar, wind, and so on, it really is feasible that we can make an impact in the real world by transforming CO2 into molecules, whether that's with chemical catalysis or biocatalysis.
Yeah, one of the things that I think is interesting is that we think a lot about, when we think about CO2 as a synthon, people think a lot about climate change and the like, but I think for me the stronger drive is when we stop sucking oil out of the ground to burn fuel in our cars, we will also stop sucking carbon out of the ground in order to make all the products. And actually that's the view that I kind of, the lens I see it through is actually we do need to find alternative sources of carbon. And so might as well be CO2. Okay, so talking about alternative sources of carbon, our next clip is from Professor Herbert Sixter of the University of Aalto, who has been developing new processes to minimize the pollution caused when processing wood pulp into paper.
Commercially, there are only two processes available at the moment. The one is an acid sulfide process, where sulfur dioxide in an aqueous solution, together with salt like sodium hydroxide or magnesium hydroxide, delivers a very powerful nucleophile, hydrogen sulfide, which is very selectively reacting with the lignin, thereby solubilizing the lignin. And after phase separation, what remains is a so-called pulp, which consists of cellulose and hemicelluloses. The other one is the so-called Kraft process. That's the dominant process, which uses sodium hydroxide and sodium hydrogen sulfide. There, the powerful nucleophile is the hydrogen sulfide, which reacts also with the lignin and basically allows a very selective removal. In both cases, the big drawbacks is that we have to use sulfur compounds, which lead to all kinds of nasty byproducts, both in aqueous and in gaseous emissions, and very difficult to basically avoid any of those emissions. So even though there are a lot of so-called abatement technologies available, there is certainly a residue which goes into the environment. That's the first drawback. The second is that the investment costs for such a plant is extremely big. So a typical 500,000 tons per year production unit is more than 1 billion euros. That means the economy of scale requires also a very high amount of production. So, and the third one is, of course, also that typically only the cellulose fraction is used, whereby the rest of the lignocellulose, and lignin is basically burned. Of course, the generated energy is utilized for the process, but it's very difficult to utilize the byproducts, sugar-based byproducts or lignin-based byproducts. So these three disadvantages drive us to develop novel and more environmentally friendly processes, which also allow a lower economy of scale, so in the range of 100,000 tons per year, with a much lower investment costs, and secondly also to avoid any sulfurous compounds, and thirdly also to allow the recovery of the side products and convert them to value-added products.
So a great contribution on our ability to access biomass for resources. Fran, what did you think of this?
Oh, this was really good. It touched on so many of the sustainable development goals. So you can think of SDG 7 with energy, number 12 for responsible consumption, and SDG 15 for life on land, and probably more that I've forgotten. And lignocellulose is a really important material for developing renewable materials and chemicals. This paper that focuses on a particular sort of wood as the feedstock of birch could be modified and attempted on other lignocellulosic biomasses across the world. And so I think it highlights how often with new sustainable technologies, we need to think regionally and locally to make sure that we're developing the right technology for our area. And this particular paper, it was using so many what I would call green technologies. So it was using gamma-valerolactone as the solvent for this organosolve type process, which is a green biosourced solvent. And so this kind of moves on from some of the other solvents that are used in this sort of process that are perhaps less sustainable. And I thought it was interesting in Dr. Sixter's comments where he was talking about the separation of these different components in lignocellulose. So the cellulose that has predominantly been the focus, but hemicellulose and lignin that are often overlooked. And something that some people are unaware of in the chemistry community is that separations like this are really, really challenging. So it's great to see progress being made here. Separations are typically very energy intensive. And so developing technologies to separate these three components from lignocellulose is really good. But also Dr. Sixter pointed out that it's still hard to avoid all emissions. So I think sometimes we can be hard on ourselves, or the public can be hard on us, because nothing's perfectly green. We haven't got the perfect answer to these problems. And yes, we can't. We need more people to go into science, chemical sciences in particular, to help us achieve net zero and help us avoid emissions.
Fantastic. John?
Yeah, I mean, I think once again, this points to where we overlook the impact and the relevance of chemistry in our everyday lives. You know, we're increasingly becoming digital, and yet the craft process that Professor Sixter pointed towards, and his technology as an alternative, processes 130 million tons of pulp every year, and is globally relevant. And we take that for granted. It's the same way with the energy system, we put our focus on electricity, thinking about solar PV and wind turbines, and we neglect the importance of the role of heat in our homes, in our daily lives, and in our industrial processes. And again, so improvements in the chemical fundamentals that allow us to reduce the amount of heat required in processing some of those materials that are used every day around the world has the potential to add up to really significant difference.
Yeah, I agree, and I particularly our listeners might well be. I would expect them to be familiar with cellulose as a sugary polymer, but might be much less familiar with lignin, which is a really complex aromatic polymer. And I recommend you Google its structure and have a look at it. The idea that a compound as beautiful as that gets burnt as waste is anathema to me. You can see how in our post-petroleum world, you have to think, where will we get aromatics from? We will get them from lignin. And so having technologies that we can process the biomass and recover the lignin in a usable form are so important. Okay, and so finally, we're going to hear from Professor Andy Abbott of the University of Leicester, and he's part of the Faraday Institution, the focal point for battery science and innovation in the UK. And this paper looks at using the systems he invented, I should say, deep eutectic solvents to recover precious elements from waste electronics.
Yeah, so we're part of several projects which are funded by either Innovate UK or RSC UK. And what the government is trying to do at the moment is to look at a suite of elements called technology metals. And these are particularly involved with our drive towards sustainable energy production. So things like photovoltaics and printed circuit boards, batteries, and also wind turbines particularly. So what tends to happen is that these are very metal hungry in terms of the elements that they use. So a wind turbine, a relatively small wind turbine, has over a ton of rare earth magnet at the top of it. And again, things like photovoltaics will be very dependent on a wide range of different elements, things like silver, in many cases it's elements like tellurium. And what current techniques will do is dissolve absolutely everything in the liquid using things like aqua regia as your digesting medium. What we're trying to do is to learn from biology and geology where they use earth abundant elements to do the catalysis. So just about everything in biology involves elements like iron. And so we're trying to take earth abundant elements and to use things which can be regenerated, hopefully by oxygen, which is the way in which biology regenerates its catalysts. And we're trying to get processes which are extremely rapid and selectively dissolve the elements of interest and leave the elements that we're not trying to get, obviously in the solid form. It's part of a suite of papers that we're putting together. So the concept we're trying to look at is, rather than dealing with batch scale processing where you use a very strong oxidizing agent which oxidizes everything that's in your system, and usually the metals that you're interested in are there in very low concentration. And so what tends to happen is once you've dissolved a small amount of metal, it's very hard to recover the metals again. So what we're trying to do is develop selective leaching techniques whereby you can leave the more base metals in there, so things like aluminium and copper, and you're able to then extract the more valuable metals, get those into a concentrated regime, and be able to select one metal with respect to another metal. In this specific case, what we were looking at was the most common sort of solar cells, which were to do with obviously silicon. And we're trying to look at the valuable metals in there are silver. The silicon is very difficult to recycle because it's got a layer of silver on the top, it's got aluminium on the back. And what we developed was a sort of two-stage process whereby we could selectively pull off the aluminium and leave the silver there, and then we could then recover all of the silver. We're trying, as part of a project which is UK funding called Met4Tech, we're trying to develop a series of these processes which can selectively separate out the elements. And the flow diagram that we've got in there gives a suggested method by which silver could be separated from aluminium without there being any contamination between the two.
So there you go, another great paper from Andy. And what I like about this paper is that it tries the challenging substrates. It recognizes that we don't in our technologies, as I look around me, my calculator, my mobile devices, we don't have just one metal at a time, and we have complex mixtures of these, and that's what needs to be separated. That's why the recovery is so difficult, and the flexibility that the deep eutectic solvents give to being able to tune the solubility of different metals and the etching rates that they're seeing, particularly with just something as simple as changing the amount of water, I think is a really elegant way of approaching this huge problem of how are we going to mine our own electronic devices to get the metals that we currently get from digging them out of the ground. Fran, John, what do you think?
I found this really interesting. I'm involved with IUPAC, the International Union of Pure and Applied Chemistry, and we have a lot of projects on around the world related to e-waste, and particularly reaching out to countries in Africa and Asia where it's a huge issue because a lot of the developed countries are exporting their waste there because regulations aren't as good. And so you can imagine, as Andy mentioned in his clip, using aqua regia, this really caustic mixture of acids, having people who aren't trained to use that and hurt themselves badly. So I thought this technology has a lot of scope, and as you mentioned, this being able to separate a mixture is just so cool.
And can I come in there, Tom?
Yep, please do.
I mean, so I think this points towards an issue that the Royal Society of Chemistry has been raising for a number of years now, and we have a microsite around precious elements and about the recovery and the importance of the diversity of elements in our electronic devices, but also to the breaking news from COP27 today. The Global Carbon Project has reported that emissions have gone up again, admittedly by a relatively small amount after last year's rebound, but most of the growth has been associated with increasing oil consumption. And people often point towards both the sourcing of metals and the disposal of metals as a barrier to delivering an electric transport system with more electric vehicles of all different shapes and sizes. But it's absolutely vital that we do that so that we have mobile energy storage that's available to get us around, to help our economies to function and our lives for us to live flourishing lives without consuming the enormous quantities of oil that are leading to dangerous climate change. And so having these disposal techniques and technologies in place before we are processing very large industrial scale quantities of electric vehicles, batteries and electronics is absolutely vital.
Thank you. And who would believe that the time would be passing so rapidly? So we've had some questions come into the chat. I think we might have time to squeeze one of them in. And so Sanaya Samlali asks whether green chemistry produces non-sustainable and toxic intermediates and byproducts. Fran, what do you think?
I think the whole purpose of green chemistry is to avoid hazardous chemicals and processes, and whether that's as an intermediate or a byproduct. And therefore, if during the research stage it was discovered there was this toxic intermediate or an undesirable byproduct, we wouldn't be considering it green. And therefore, you'd have to go back to the drawing board and try a different approach. And so I really like the concept of benign by design, and the fact that you can go back to the drawing board and make these changes. I think one thing that green chemistry is really good at is finding uses for byproducts, whether that's CO2 that's being generated somewhere that's been a part of the discussion today, or something else. I think byproducts and using them is important. And yeah, no toxic intermediates, please.
Yeah. Well, actually, the questions come in. I think we can squeeze in another. Questions come in that's in my area of expertise, and so that's from Basharat Ali, who's saying that most synthesis labs use organic solvents extensively. And is there any research done for selective separation or recovery of these? And the answer to that is definitely yes. There is a whole range of research, from replacing the current solvents that we use with ones which are inherently more benign. Indeed, separation techniques, so that we don't just commingle all of our solvent waste and then leave it as the only alternative is to incinerate it. So there's a huge effort across many laboratories across the world in that area. But time is marching on. And so I need to say thanks to Fran and John for joining me today. But before I completely wrap up, I'd like to introduce the executive editor of RSC Sustainability, Emma Ely, to tell us a bit more about the journal. Oh, have we lost Emma? Okay. Oh, here she is.
Here I am. Brilliant. That was an unexpected technical glitch, but I'm really glad to be here today, Tom. So thanks for the introduction. And as Tom pointed out, I am Emma Ely, and I am the executive editor for the RSC's new journal, RSC Sustainability. And on behalf of the whole RSC, we're really pleased to be launching this new journal as a key title aimed at addressing the Sustainable Development Goals. And we really envision that this new journal will give solutions-focused research the open access platform necessary.
Okay, so I shall step in now. And just to say that the journal is now open for the submission of papers, and that we look forward to receiving them from you. You should know that for the first 2 years it is not only open access, but it is free to publish in. So for me to finish for today, thank you very much again to Fran and John for joining us. Of course, thank you to the wonderful authors of our fantastic first 4 papers. And I need to do a plug. Don't forget to join us next week on Tuesday, the 15th of November, for our next Sustainability Live session, which is going to be on RSC, EES catalysis, hydrogen solutions, and COP27, which will be starting at 1 p.m. And on Thursday, the 17th of November, you'll find the final broadcast in the series, RSC Sustainable Food Technology and COP27, here on our YouTube, LinkedIn and Twitter channels, also at 1 p.m. GMT, I should say. And make sure that you subscribe and follow us on social media for more of our sustainability work, and listen to our Brought to You by Chemistry podcast, with recent series covering big issues in plastics and batteries. And finally, have a fantastic day wherever you are around the world. And thank you for coming to join us. I saw 4 continents in our listenership, And so isn't that amazing? Thank you very much, everybody. Goodbye.